So yeah, I'm going to give an overview of a project that is in its second year now, and I'm going to start by setting the context. So first introducing how the interaction of geology, crop production dynamics, the saturated thickness of the aquifer across the region, recharge rates, and shifting climates are impacting the current state of things, where we have hotspots of groundwater depletion, and then move forward to most of the talk today will be on the so what, now what do we do with that information that we have given that context. So, quick overview of what the Ogallala Aquifer is. It is one of the largest groundwater aquifers in the world, and the Ogallala Aquifer is actually a sub-formation within the broader High Plains Aquifer, and the Ogallala just has a nice ring and it has a lot of cultural associations with it, so that's the term that our project is using, but in reality we are talking about the geologic formation of the High Plains Aquifer, which underlies 8 states in the U.S. and is more than 174,000 square miles in area below those 8 states, and it's a major water source for both the rural communities as well as agriculture in that region, and we've been using it for about 80 years now. And it's a very critical agricultural region, both within the U.S. but also globally. The aquifer supports about 30% of U.S. crop and livestock production, and a big part is the livestock piece, that we have a very high concentration of livestock within the Ogallala Aquifer region. And this sort of outlines the broader region of the aquifer, which generates about $35 billion in agricultural products annually, and it's thought that groundwater use directly contributes about $12 billion of that productivity in that region. It is mostly in terms of irrigated crops. Irrigated corn definitely dominates the northern half of the aquifer. That's the yellowish color here you see. This is a croplands data layer from 2016 of the region. And then the red areas you see are cotton irrigated mostly, as well as dryland cotton in the southern region of the plains. There is quite a bit of dryland, non-irrigated cropland in that area. So the 45 million acres in the Ogallala Aquifer region that are cropped, about 27% of that is irrigated. And then there's an additional 50 or so million acres in pasture and range. So it's a diverse area, but definitely the irrigated cropland is a big driver in terms of the yields, the productivity, the livestock feed in that region. And so that one thing about the aquifer that's often not talked about when people think of or hear about declining groundwater levels is that it's not uniform at all. So this map here shows the variation in saturated thickness, which is basically how much water is below ground across the aquifer. And then on top of that, we've layered sort of where our project is doing its work in terms of the green spots are sort of our hub research centers and institutions, and the goal was to have our activities spread across this diversity from north to south across the aquifer, where we have much greater saturated thickness up in that Nebraska area and much lower towards the central southern plains of the aquifer region. And it's not just that there's lower saturated thickness in that area, but it's also that there's very low recharge in those areas. So that means that the sand hills in Nebraska, where you see the deep blue in the northern high plains, actually get quite a bit of water replenishing or draining through those sandy type soils, as well as higher precipitation coming in. So they have higher precipitation in that northern region that helps sustain that greater saturated thickness in the north. Whereas we move to the south, and this map doesn't include the tip, but the southern high plains in general has very low recharge rates, which means that there's basically not really sustainable pumping. There is no option in those lower areas where you have recharge of 2 to 5 or less millimeters per year of water going back to that aquifer to sustain any type of irrigated cropland without some level of decline of the aquifer. So it depends where we're looking on the aquifer, whether there is sort of a sustainable use with irrigated agriculture whether that's feasible or whether we're really looking at extending the life of the aquifer rather than sustaining it. And then layered on top of that is the fact that our climates have been changing. So we definitely have a climate gradient regardless across the aquifer. Obviously it's a lot warmer, higher potential evapotranspiration in the south compared to the north. But this is data put together by Zhao Malin at Kansas State University on historical weather records over the last 115 years across the aquifer. And I specifically just chose the minimum temperatures to show. The left figure here is during the corn growing season, so mainly summer temperatures, whereas the other one is winter wheat, so that's fall up until spring. And what we see, because the reason I showed this figure is that it's the minimum temperatures that we're seeing the biggest shifts historically, and where we expect to continue to see shifts into the future, that we are increasing temperatures, minimum temperatures across that, especially during the winter months. And this has major implications for evaporation, precipitation dynamics are also inconsistent across it, but in particular crop growth and evaporation are really going to be impacted by increasing temperatures moving forward. So if we pull these pieces together of geology, the amount of water we're pulling out from different regions to support crop production, and the variation in recharge rates, as well as the climate variation across them, this is what sort of brings us to where we are today, where we have hotspots of groundwater depletion across the aquifer. So this shows water level changes from pre-development, so around 1950s up until 2013, and we have a variety of recent analyses that show similar patterns where we see we don't have huge depletions in a lot of the northern High Plains, Nebraska region, but especially as we get into southwest Kansas and Texas, we've seen substantial changes in terms of water level, saturated thickness, and there are areas that no longer have sufficient water to support irrigated agriculture. They might have enough water to support municipal wells, which have a lower demand on the water. But once you get below a certain level of saturated thickness, it's economically not viable to pump water for irrigation for agriculture. So we have this variation across the aquifer in terms of where we are today. And then on top of that, our management is very decentralized of this groundwater. Each state has different approaches to how they manage groundwater in terms of water rights. And then also states, with the exception of Oklahoma, but most states have regional groundwater management districts or resource districts. They are the ones who set policy and targeted well permits, and as well as sort of targeted in terms of how much pumping is allowed moving into the future. So in many of these groundwater management districts, there are targets set for where they know depletion is happening, but they will set a target, 10, 20 years out of what that depletion rate will be to try to minimize or extend the life of the aquifer. So the decision making across the aquifer is very decentralized, and that can make things a bit challenging. And then because of that, you see a lot of variation in terms of pumping limits that are set at that local and state level. So this map here really tries to show the variation where in that high saturated thickness area of Nebraska, there basically are not limits set out by these management districts for pumping. Most other areas as you move south do have some pumping limits, but they really vary in terms of the inches per acre per year that can be pumped. And where you see some of the smallest dots, like in southern Nebraska there, where there are pumping restrictions of 9 to 12 inches per year, that's actually the complex interactions between surface water and groundwater, where because of state compacts between Nebraska and Kansas related to the surface waters, and because there's an interaction between groundwater and surface water, they've had to set more strict limits on pumping to meet those cross-state compacts. And we'll talk about that a little bit later in this webinar as it relates to the Republican River Basin in Colorado as well, which is impacted by compacts with Nebraska and Kansas. So we have a lot of variation across the whole region in terms of what sort of policies are in place and incentives and limits on water use, well permitting, and all of that. So that's where we are. We sort of know how much groundwater we have to a large extent. We know how much, we have pretty good estimates now on how much used to be there. And so the question is now, how do we manage this moving forward now that we have a pretty decent characterization of the groundwater? And that's really where our project comes in. So we, as was mentioned at the beginning of this, we're part of a USDA NIFA-funded project that's one of these CAP grants, which is called, it stands for Coordinated Agricultural Partnership. And these are designed to be broad, multi-state, multi-institution projects to tackle some of these larger problems that cross state lines. And so our team has more than 40 scientists across the 9 institutions represented here across the bottom of the screen, across 6 of the 8 states of the Ogallala Aquifer region. And we also have a very strong advisory board that represents farmers, groundwater management districts, industry partners across those states as well. This image here is from one of our first planning meetings when we first started. Our team continues to expand as we bring in new graduate students, postdocs, and others that are on the team. But one thing we try to keep in mind is what can we offer as a cross-state team that the individual institutions can't do on their own? And one of the main things is that each state is different. Their context is different. Their geology, climate, groundwater management might be different. But at the same time, we're grappling with very similar issues across state lines. And so how can we learn from each other across those boundaries? How can we avoid duplication of our research efforts and leverage synergies? So as much as we're doing some new research, we're also doing a lot of work to synthesize the existing research that's out there and data sets that are already out there to develop some decision support tools. And then as we do that, we're building collaborative networks, both within our team but also with producers, groundwater managers, policymakers, industry, a broad range of stakeholders moving forward to try to have a more unified conversation about this shared resource of the aquifer. So some areas where we think that we can have impact is because decision-making and policy-making is decentralized, both in terms of groundwater management districts, but also because it's individual producers making day-to-day decisions on crop management and irrigation management decisions, that we really are trying to ground our work by engaging with producers and groundwater management groups individually as well as collectively across the aquifer. And then there's a lot of technological advancements and tools out there that farmers are using or trying or considering. And so our goal is to partner with industry some to help move some of those technologies along, validate them, and bring them into different innovations in water management. And then more than anything else, I think in general, it's been really hard to ask some of the difficult questions that hopefully our project can start to ask. Is what is the value of water both today and into the future? And what are the options looking forward so that communities that are having declining groundwater so that they can plan for the future and understand some of the different options and the different consequences of some of those options moving forward. So basically we've characterized that there are multiple levers we can pull on to shift how groundwater is used. And again, with this end goal of sustaining in some regions or extending the life of the aquifer while also maintaining viable livelihoods for producers and rural economies. So we're going to look at irrigation management technologies, different scheduling tools that are out there, what are options under limited irrigation, and I'm going to go through each of these in a bit more detail, but evaluating policy management scenarios. And then our other goal is to try to be sort of a middle broker of information across the aquifer. So there are many levers we can pull, and I think one of the questions is, which are going to have the greatest impact? Where should we allocate resources? Where is feasibility better? Where is adoptability easier as we move forward? So in terms of management levers, one of the main things is just how we do our irrigation, that we can improve water use efficiency just by how water is delivered to the field. And so there's a variety of emerging current practices and technologies. So center pivot is shown in the image here. Center pivots is the predominant way that irrigation is delivered across the aquifer. But there are lots of new approaches to how those center pivots operate, whether it's variable rate irrigation, where those different sprinklers can adapt to soil conditions, or the spatial variability in the field, basically to irrigate at different amounts based on the crop growth in that region of the field. So similar to precision ag with nutrient management, there are tools now being developed for variable rate irrigation management. I would say that those have mostly been looked at in areas with higher saturated thickness and less in areas where there isn't enough water to really meet full crop ET demand. So especially there's a lot of active research on variable rate irrigation in the northern part of the aquifer region. Another technology that's been around for a while but is still being sort of reevaluated and technology is being improved, or the equipment's being improved, is mobile drip irrigation, which is also in the image here where you see the orange drag lines coming off some of the sprinkler nozzles. This is some work that one of our collaborators on the team, Isaiah Kiseka, has been working on in Kansas, looking at comparing sprinkler heads to drip lines pulling through the field, and his study did show that there was about a 30% decrease in evaporation, soil water evaporation, with that mobile drip irrigation. However, same time, we need a lot more data to really understand what the net effect is in terms of water use efficiency and the value of some of these different technologies. So this is an area where there's been a lot of research over the years that we can try to synthesize and look at the relative potential of some of these different irrigation technologies to improve water use efficiency. Subsurface drip irrigation is another big one that we're seeing adopted more in limited water, so lower saturated thickness environments of the southern high plains, for cotton production, for example, in in Texas, or some corn production systems in Oklahoma. And so looking at there's a big upfront cost in installing subsurface drip. Where is the trade-off and the benefits in terms of how we manage that? And of course, then we have a lot more flexibility in terms of the timing of when we apply water. So scheduling couples with those different technologies. So those are some examples of some of the different emerging irrigation technologies that are out there. Another huge lever that's been sort of intractable is scheduling irrigation, where by and large, for a variety of convenience, cost, risk management reasons, a lot of center pivot irrigation is done on a fixed schedule. And we know that we could improve efficiencies quite a bit if water was timed more specifically based on soil moisture and actual crop development, or with short-term weather forecasts brought in if there's an upcoming precipitation event coming, not irrigating, for example. So there's quite a few tools that are out there, whether it's the Texas DM model that's being developed looking specifically at cotton production, cotton irrigation systems. K-State has the CanSched scheduler, and Colorado State's developed this WISE irrigation scheduling tool, as well as a mobile phone app. So one of the things our project is trying to do is to improve these tools, and by cross-state collaborations, try to figure out where we can streamline and improve data across these different platforms and not duplicate efforts. And the other piece, so there's a lot of work going on in validating and improving these. And then the other piece is improving their accessibility and their adoption by farmers, and understanding what it is that are the barriers to increased adoption of these different scheduling tools, and how we can link them more, streamline them a bit more with their existing irrigation systems. The other piece is that a lot of the irrigation scheduling tools are based on this estimated evapotranspiration based on existing climate data for that year, but historical or data sets understanding crop coefficients and how crop production varies across the season to estimate water use. But the reality is that we have better and better tools now to actually get real-time feedbacks of how much water the crop is actually using to get more precise scheduling. And a couple of those ways, one of them is through soil moisture sensors that are being developed. So they're more available on the market, and one of our collaborators, Darren Rudnick in Nebraska, has been comparing and evaluating some of these different sensors on the marketplace and looking at, because of cost, it's not easy, or logistics, it's not easy to have 50 of these in one field. So, you know, how well can we calibrate them and rely on them when only one or two is installed in a field? So we need improved ease of the calibration. And then integrating those tools and that data back with our irrigation scheduling tools. So that's an area of research that we're actively looking at our team, is soil moisture sensing to inform irrigation scheduling. On top of that, the other way to approach that and understand crop water use in real time is to measure actual evapotranspiration remotely. And so Jose Chavez on our team has been working on using unmanned aerial devices, to drones basically, to fly fields and assess actual real-time crop water use or evapotranspiration, the water coming off of the field. And the question is, can we use that in the future to feed back to scheduling tools and understand as crops develop how much water they're using, therefore how much water needs to be applied through irrigation. So those are sort of the actual mechanics of irrigating, the timing, the placement. There are many other management levers that we could use, you know, that impact water use, whether it's as water becomes more limiting, especially in the southern high plains. They're looking more at limited irrigation systems, same with the regions of eastern Colorado, where it's really a question of not when to irrigate necessarily, or how much or how to get all of the water that the crop needs to it. But if you don't have enough to supply the full demand of the crop, when are the ideal times and amounts during that crop growth to deliver water? For example, we know from research actually out of the USDA group here in Fort Collins that there's a key time during vegetative growth to apply irrigation water, or where irrigation water can be reduced and still maintain yields if water is then returned during reproductive phases. So timing of irrigation in limited irrigation systems is a key research area, and then developing and improving our crop water production functions, those crop coefficients I was talking about that just go into the irrigation scheduling tools. We need better estimates of crop water use under limited irrigation so we can more effectively manage water in those crops. And then there's soil management is a huge piece, as well as what crops we actually grow. So one example of that from Oklahoma, led by Jason Warren, who does more cropping systems work, and Art Stoker, who's an ag economist. They've paired up to look and evaluate at what point does sorghum become a better choice for producers over corn. So irrigated corn has a really strong response to water availability, a really steep curve. Add more water, you get more corn yield. Sorghum, however, tends to be a relatively more drought-tolerant crop in terms of production. So this figure here just shows that as the irrigation capacity, so the well capacity declines, the net revenue, the y-axis here being the net revenue of corn versus sorghum, the sorghum becomes more profitable at lower well capacities, as opposed to corn being more profitable at higher well capacity. So understanding where those trade-offs are for producers and understanding what policies are in place to help incentivize wise crop choices for producers is something that's also an important lever that we look at moving forward, is what crops are we growing, and does that crop choice change based on the water availability in the region. And then definitely how we manage the soil is going to be increasingly important. There are areas where we definitely are already seeing transitions from irrigated to either limited irrigation or even in some areas dry land production, so production without supplemental irrigation. And in those situations, the ability of that soil to infiltrate rainfall events, to hold on to water events, becomes increasingly important. So soil health is going to be another piece in this mixture of how we improve water use efficiency across that. And so we have some other research looking at how soils change as you transition from full irrigated towards limited and dry land. How do we maintain good soil quality in those situations and maintain soil carbon in those situations to sustain higher productivity in our dry land or limited irrigation cropping systems. So to kind of summarize some of the management levers we're looking at, the goal is that, if we can understand the relative potential impact of a variety of practices on water use and productivity, we can then help producers and policymakers prioritize what sort of incentives are out there or what different practices are adopted. So in a win-win world, we'd see increasing feasibility of adoption of practices that have the highest impact on reducing groundwater withdrawals while sustaining production. But the reality is that as the easier changes to make often are those that have smaller relative impacts and or the really, for example, adoption of irrigation scheduling tools has been really hard to increase, even though we think it could have relatively high impact. So how do we shift this balance between feasibility of adoption and their impact on water use moving forward? And part of this, in terms of looking at these, is really going to be, this is where we get back, engaging at the ground level, is partnering with management districts that are evaluating options moving forward, looking at what, if they are going to target lower groundwater withdrawals in certain districts, what are some of the best options to prioritize, both from management but also from a policy perspective. And so this is where we're pulling on some work that was ongoing before our project started, looking at the Republican River Basin in eastern Colorado that runs into Nebraska and into Kansas. So this is part of that three-state compact area where surface water is interacting with groundwater. And so there, a group of agricultural economists here at CSU, led by Dale Manning here, partnered with the Republican River Basin to evaluate different policy scenarios moving forward, where their goal was to extend the life of the aquifer by reducing pumping by 25% in that region. And so they could connect both a groundwater model and an economic model and a crop model to look at the economic impacts of different policies basically on to achieve that target. And so the graph here shows the percent reduction in groundwater extraction, not changing crops, not changing management practices, but more if a farmer was faced with a target of reduced groundwater withdrawals, what might be the most feasible in terms of the policy to incentivize that would cause the producer a lesser reduction in income. And so what they found was that they compared a flat across-the-board quantity, so a pumping restriction limit is the blue line, or a set fee on pumping, the red dotted line, or something more based on the land area basis, an irrigated acreage fee to, again, incentivize reduced water withdrawals. And what they found was, in terms of the percent reduction in agricultural profits back to the producer, that the pumping fee was the lowest cost way to reduce groundwater use across the basin in the short run. And so this type of analysis is an example of what we're moving forward with in this project. So we are going to be doing a series of evaluating the relative impacts of both crop management decisions, some of those irrigation management decisions I just highlighted, as well as different policy options. And again, grounding this back to individual or regional groundwater management districts, where we're linking hydrologic models, in this case ModFlow, with a crop growth model to economic models to run a bunch of what-if scenarios, both on terms of crop choice, improved crop genetics, as well as those policy options of water restrictions or using different incentives, and running those both under current and future climates. And the goal is that out of this, there'd basically be a decision support tool that could be applied in different ways to do those sort of planning exercises of what if for different communities moving forward. So in more detail, what this looks like is we're linking the ModFlow model with the DSAT cropping systems model with the surface water model, in some cases SWAT, and then into those pieces, and this work led by Ryan Bailey here at CSU, as well as Prasanna Gowda, Isaiah Kiseka, and then linking that in with the ag economics models moving forward to evaluate the relative impact of different policies and managements. Again, coming back to this idea of what are the levers that we can shift that will have the greatest impact but also sustain livelihoods moving forward. And so we're starting that with a case study example in Finney County, Kansas, near Garden City, Kansas, where we can get maps like you see here on the right of your screen of existing irrigated croplands and what's grown in those areas, corn being the more yellow, alfalfa being the purple, which is one of our challenges. Current crop model doesn't include a module for alfalfa, so that's one thing we're actively working on as well right now. So we're using this as a case study example because that region already has an existing groundwater model developed by the Kansas Geological Survey. So we can use the groundwater model with what we know about where pumps are within that region, what crops are grown there, to understand what pumping is coming out, and then we can use that information to then run about a bunch of what-if scenarios in the future to evaluate the linkages between management changes and actual groundwater extraction over time to, again, try to be able to say, okay, if X is adopted, it might have Y effect in this region. So this is a really novel new integration of different models to help with decision making. And then on top of that, there's a sociology piece of this whole puzzle as well in terms of understanding and even how the assumptions we make within our models in terms of what the value of the water is today versus the value of the water tomorrow. And so some of the questions, we're going to be sending out a big survey this winter to stakeholders across the region, replicating somewhat a survey that was done about 25 years ago in the region to ask some questions, what would it mean to be unable to pass a viable operation to the next generation? What is really being saved in that region, that community, when water is conserved? Because there's plenty of economic incentive to use it today. Is there value? How do we place value on the value, on saving it for future generations? That's a much more difficult piece to put a dollar number on, and it really comes down to more social and cultural beliefs and values as we look forward. And all of this, throughout all of these different pieces, keeps coming back to how do we engage with producers and key stakeholders that are making these decisions day to day. And so that's a huge piece of what we're doing as well in terms of facilitating producer industry partnerships, doing on-farm testing, linking with stakeholders throughout the region. And with that, I'm going to put a big plug out to a webinar that's coming up in a month from now by other members of our team. And they're going to be talking about some of these innovative approaches that are being used, whether it's water technology farms in Kansas or a really novel competition that they're running out of Nebraska where different farmer teams are competing with each other by choosing management practices that the research station is implementing in a replicated experiment, and they're going to see who can choose the best management practices for improving water use efficiency in a corn crop with a variety of different technology options at their disposal, as well as a whole network of farmers in the Texas area through the Texas Alliance for Water Conservation that have been collecting and sharing data among themselves for quite a number of years now, and what have they learned from that network of peer-to-peer learning. So I would encourage you, if you want to hear more about some of these extension efforts, to join that webinar next month. And then some other things we're doing in terms of partnerships with other organizations is partnering with USDA Climate Hubs, as well as the Drought Mitigation Center and other entities, and we've started holding listening sessions. So we did one in Clovis, New Mexico last year where we got a diverse set of stakeholders, ranchers, farmers in the room to talk about the 2012 drought in the area. So one easier way to talk about climate is to look back through time and look at climate extremes that have happened in the past, how they impacted production, how people have rebounded or not rebounded as well from that drought, in a way to think about managing risk, looking to the future where droughts are predicted to happen more frequently. So that was a really useful and engaging type of event where it's a bit of a listening session, so we get ideas and information from producers, but then there's a lot of peer-to-peer conversation on risk management related to climate moving forward. We're not the only folks working out there in this space, and so we're trying to build networks with existing Ogallala Aquifer partners. For example, the Ogallala Aquifer program, that's an entity that's been going for more than a decade, mostly in Texas and Kansas, is a strong partner on our team. We have a lot of overlapping team members. The Ogallala Aquifer Initiative through NRCS that incentivizes different practices, as well as USDA Climate Hubs, are key partners in our work moving forward. So at the end of the day, we hope that we can be sort of a go-to source of information on emerging tools like technologies, events, research around the Ogallala Aquifer. So one other tool that we're trying to develop is a bit of a comparison shopper tool about some of these emerging technologies. So that's something hopefully we'll have developed in the next year or so, where we have, whether it's irrigation scheduling tools or soil moisture sensors, a place where producers and others can go to say, what does this one do? What are the options out there? And provide some of their own feedback and ratings through that system moving forward. So at the end of the day, some of the hopes from this project are that we've developed new and expanded producer and research networks, improved tech tools and technologies for water management, as well as increased producer engagement and water conservation across the region, and then informing regional planning efforts through this decision support tools and or just through listening sessions and conversations, whether it's going in, we've talked about our project to dairy farmers or young farmers associations, just beginning to start asking some of these difficult questions so that hopefully they're not as difficult to discuss and communities can be forward-thinking about declining groundwater levels and how we can extend the life of that shared groundwater resource moving forward. And with that, I'm going to wrap things up. Here's contact information for myself. Reagan Wascom is the co-project director with me on this. Amy Kremen is our project manager, who really makes everything run and keeps the website. And we also have a Twitter feed. We would love to have people join and share. We also have a newsletter. Those all can be accessed through our webpage, ogallalawater.org. And with that, I would welcome any questions.